So I'll take questions that you have on that first, if there are any questions.
Oh, there's a lot of questions.
There's a lot of questions? Thanks.
I do not understand proving things at all.
Okay. So where would you like to begin?
I just don't get how you jump in between, like, you go from that starting equation
Uh-huh.
and prove it, I guess. Right?
So is there a particular problem that you're talking about right now?
No, it's really, I don't understand it at all.
Okay, so what practice exercises have you been working on?
Just the first few. I haven't had time this weekend. I've been having to fix my computer all weekend.
Okay. So we've got some sets. Oops. So there's I guess a set theory proof here. There's one that's one of De Morgan's theorems that we did in class. There's a set theory, and then there's a couple of Boolean algebra proofs. So I guess which ones have you tried, or like how far? What was your sticking point?
I tried 9 and I just kind of gave up.
Okay. Oh, okay. So that's a counterexample one.
I guess it's 10.
10? Is your microphone not on? Can you hear me? In Williston, can you hear me?
Yeah, I can hear you,
Okay.
but I can't hear the questions that he's asking.
Okay, we have to make sure that we turn our mics on, otherwise we're kind of excluding half the class.
Are you recording it?
Yep, thank you for asking. So the question that was just asked was, am I recording it? Let's just have our mics on. Everybody just turn your mic on. Literally, like everybody, like that is actually helpful. It will lose less time in having to ask a question 2 or 3 times to make sure that everybody heard it. So you said that you tried number 10.
Yeah.
Okay.
First proof is all I remember.
So it says prove that for all sets A and B, if A is a subset of B, then A intersect B is equal to A. So if A is a subset of B, then A intersect B is equal to A. Okay. So it's an if-then proof. An if-then proof, we're just going to suppose that the if statement is true and then show that the then statement is true. So here's our proof. Suppose A is a subset of B. What does it mean to say that A is a subset of B?
All elements that are in A are in B.
Yeah, right? And so sometimes it can be helpful to paraphrase what something means before we actually invoke the fact, right? It can help us, kind of prime us for thinking along the lines for making this fact useful. So all elements in A are also in B. Okay. The then statement, right? So here's our if statement that we started with. Here's our then statement. We're going to show that 2 sets are equal. So to show that 2 sets are equal, we're going to have to show containment both ways. So we will show that A intersect B is equal to A. So we're going to do this in 2 parts. Right? There's 2 parts to this. We're going to show that A intersect B is contained in A, And the second part, we're going to show that A is contained in A intersect B. And a lot of these I don't think will take a lot of arguing, but we're going to cite a few facts and draw a couple of conclusions. So for the first one, if we're going to show, right, we're starting with this one, we're going to show that A intersect B is contained in A. And this is almost by definition, really. In order to show containment, we grab an element on one side. So we'll say, let's let X be an element of A intersect B. This part of the proof is going to be like really fast. What does it mean to be in the intersection?
That's the same.
What does that mean?
That X is an element of A and an element of B.
Right, you have to be in both? Okay. So this part is really short. Right away, we know that we find that X is an element of A. It's an A and an B, but all we need is for it to be an A, right? Like, in order to show that we have containment, we start with an element in A intersect B, and then we show that it has to be on that side. It has to be on the set on the other side. And we know that it's an A. So this means that A intersect B is contained in A. A intersect B is always contained in A, regardless of that if statement. You know, our if A is contained in B, then A intersect B is equal to A. A intersect B is always completely contained in A. It's also always completely contained in B. It has to be, right? Because you have to be in both in order to be in the intersection. The other part will be maybe slightly longer, but not too much. For the other part, I'll highlight this in green. We're going to show that A is contained in A intersect B. So we're going to let X be an element of A. And we want to show that it has to be an A intersect B. Let's note that we haven't really used the premise of this statement that we're trying to prove. The very first thing we said was suppose A is contained in B, and then we even reworded what that means. So we have this element X that's in A. Where do we also know it lives? Yeah, that's by our supposition, right? Like the first thing, the if statement that we assumed was true in the beginning was we suppose A is a subset of B. So by supposition, we know that X is also in B. We have X in A, we also have it in B, so it's got to be in the intersection. So A is contained in A intersect B. Now their powers combined, parts 1 and 2 here, we know that A is equal to A intersect B. And that equality holds if A is a subset of B. If you're stuck on a practice exercise, don't forget that there are solutions, fully worked out solutions included. So you can also kind of take a look there and see how I approach it. It might kind of help give you ideas. You might see if you could, reword some of those thoughts or see how I did it and then try to start fresh and see if you can make that argument yourself too. Other questions? Yeah.
So on part 1,
Yeah.
if X is an element of intersect B if there was A union B?
The first part?
Yeah.
So I want to make sure that I understand your question correctly. So you mean if we were trying to say that A union B is equal to A? So if A, and our supposition is the same, that A is a subset of B. So if A is a subset of B, then A union B won't be equal to A. It would actually be equal to B. And we can, so like when we're writing proofs, a Venn diagram is not a proof, but a Venn diagram can be a great way to start your thinking about proofs. So if I draw the Venn diagram that describes this problem, suppose A is a subset of B. If A is a subset of B, then if this is the B circle, A has to live entirely inside the B circle. And so the intersection where they overlap is precisely A, and that's what this says, so it kind of makes sense. If A is a subset of B, then their union means I'm going to take them both, take everything, like it doesn't have to be in both sets, but like if you're in either or. So the union would just be all of B, right? If you're in A or B, then you're in B in this case. So the union, and you could probably construct an argument, not unlike this one, to say that if A is a subset of B, then then A union B is equal to B, and kind of construct a similar type of argument here. Did I answer your question? Okay. Other questions? There's a lot of what we do in this class feels kind of uncomfortable because we're not just solving equations, which is I think what we're used to doing, or finding a derivative, or integrating a function, or whatever. A lot of what we do is trying to look for an argument that shows something's true, and there's not always a clear-cut path for that. So there's a lot of sitting in our discomfort and trying something that doesn't work, or feeling like we've hit a brick wall, and I just that's normal, right? That's doing math, as it turns out. But if you're getting stuck for a long time and you want a nudge in the right direction, you can email or text me. You could check out, often in the assigned problems there will be similar problems in the practice exercises, and you can look at those solutions too, and that might give you some ideas. Are there other questions folks want to ask about practice exercises or the assignment before we talk more about Boolean algebras?
Can we talk about number 4 in the assignment?
Mm-hmm. Okay, so I have a question here about number 4 on the assignment, and then I heard somebody from Williston says there's a question about the assignment. What's the question in Williston? Which one?
So the cardinality of a power set. The cardinality of an empty set is paradoxical, right?
No, well, the empty set has size 0.
Right, but 2 to the 0th is 1.
Oh, okay, hold on. Yep, I know what you're asking. Give me a second here. So we have a question on number 4, and also, is that problem 1?
Yes.
Okay, and problem.
Yes, that's problem
Okay,
1.
so what I'm going to do, I'll start by talking about that problem 1, and we'll just talk about the difference between the empty set and the set that contains the empty set. Because as it turns out, this is not really paradoxical, but it is weird. So the empty set has no elements in it, right? So the size of the empty set is 0. When we talk about the power set of the empty set, this is a set that contains all subsets of the empty set. What are the subsets of the empty set?
0.
A single thing that is an empty set.
It's just the empty set itself, right? Because the empty set is a subset of every set, so it belongs in this list, but there's no other elements with which to form subsets, so that's where we end.
And that's how the power rule applies, right?
Yeah, so the size of this set is 1. There's one thing in it. It's the empty set. So this is, the empty set is not the same as the set that contains the empty set. That's our big takeaway. The empty set has nothing in it. The set that contains the empty set has one thing in it. It's got the empty set. It's like you have a bag and you put an empty bag in it. What do you have? That big bag has one thing in it. It's just an empty bag. In fact, this whole idea, which is a little bit odd and feels, I don't know if it feels pointless, or it almost feels like a thought experiment to me. But this is the beginnings of how you build the real numbers from nothing, from scratch. You know, like you start by building the counting numbers, and you do that with the empty set. That's 0, and then you form a set that contains the empty set. That's 1, right? That's the size of that set. What would be the power set of the set that contains the empty set?
Still be 0.
Well, so it's a set itself, right?
Yeah.
What do we get to include? And the set that contains the empty set. Yeah, because they're different, right? So let's just note that how we determine how many subsets a set has, that 2 to the n rule works here, right? So the empty set has 0 elements in it, and 2 to the 0 is 1, and lo and behold, the number of subsets is 1, right? The set that contains the empty set. The set that contains the empty set has 1 subset. If we use this, 2 to the first is 2. Look at how many subsets that we got to list there. If I found the power set of this set right here, how many things would I expect to list? 4. 4 things. And we're going to have lots of empty sets and squiggly, curly braces to list those elements out. Pretty fun. So does that answer your question about this cardinality? Okay. And then the other question was about problem 4. Oh, yeah. Oh, okay, good. Yeah, all right. So they were given 2 sets. I'm just going to jot this down so I can transcribe it accurately. So A... Okay, so they give us 2 subsets of the real numbers. Okay. So A is the set of all x in the real numbers such that x squared minus 4x plus 3 is less than 0, and B is the set of all x in the real numbers such that x is between 0 and 6. And we want to prove that A is a subset of B. So we want to show that if you're in A, then you have to be in B. So, okay. So here's how I might start. I mean, it's a subset proof, so I would start the same way we do the other subset proofs and just say, let's let x be an element of A. And the only thing, that gets us one thing right now. Okay, there's one immediate thing we get from that, and that is how A is defined. It tells us that if x is an A, then that inequality is true. So I'm going to write that down. There's probably more than one way we could go about this, but a nice sort of clean argument to make would be to first do some algebra. I think this will factor.
+3, not -3.
Oh, thank you, +3, yep. So I think it'll factor.
x plus 4, x minus 1.
No,
Or no.
because they have to be,
Has to equal
we have to multiply out to positive 3.
x
X
minus
minus 1 and X minus 3.
Yeah, right, okay. So their product is negative, basically. And how do you get a negative product?
Gotta be positive.
Right, like one positive, one negative, yep. So there's, we could be really wordy about this. And if you really like that, that's good. But there's also kind of a slick way to analyze exactly where that expression, where that product will be negative. And I don't know if everybody teaches this, but if you took calculus with me, one of the things we do when we're curve sketching is we examine, where the derivative is positive and negative, right? You probably did that. And the way I like to do that is to make a sign chart because it makes sure that I have to do almost no arithmetic or calculating at all, right? I'm kind of lazy that way. So here's a nice way to kind of arrange this. And you might choose a different way, and that's fine. I'm not just saying that this is better, but it's just the way that I gravitate to. It's easy for me to tell where x minus 1 is positive or negative, right? I know it's 0 at 1, and then if x is less than 1, that'll be negative, and if it's greater than 1, it will be positive. And then I can do the same thing for x minus 3. I know that at 3. So now note this line here, the horizontal axis on the bottom, that's a real number line. So I got to put the 1 and 3 in the right order, okay? But I know that's 0 at 3. If I plug in something less than 3, and I subtract 3, I'm going to get a negative. And if I plug in something greater than 3 and subtract 3, I'll get a positive. And then I left room here at the bottom to put their product. So I could tell where each of these is 0. We could tell where each of these is 0 anyway just by looking at the factored thing, right? We've solved lots of quadratic equations, so we know it's 0 there and there. Does anybody want to have a shot at telling or sharing with the class how we fill in this bottom row?
Would it be minus the first 0, then plus, and plus?
Say that again.
Would it be minus the first 0, then plus into the rest of the way?
So like minus is here and plus there.
Yeah.
It's not going to be, let's see, this one is correct. Can anybody tell me why we get a plus at the end?
You multiply the sign of each of those, so there will be plus, minus, plus.
Yeah, so this is the product. This bottom row is just multiply the two rows above it. So when we do that, in the first interval, we have a minus times a minus, which is a plus. In the middle, we have a plus times a minus, which is a negative. And then at the end, it's plus times plus, which is a plus. So this is a way for us to analyze what values of x are included in this inequality. What values of x are in the set A? So yeah, so what values of x are included in this set A that we started with, right? Like we took that inequality and now we made this sign chart. So we started with this.
Less than x is less than 3.
Say that again.
If 1 is less than x is less than 3. Or sorry, 1 is less than or equal to x is less than or equal to 3.
Yeah, in fact, I'm going to go with your first one. It's actually strictly less than because this was a strictly less than 0. But yeah, it's these values in between, right? Because this was, where is this less than 0? Where is this negative? And now we can see exactly where it's negative. So they gave us this set A, and they defined it by saying, well, where this quadratic is less than 0. As it turns out, they could have just been a little bit more direct and said, oh, it's where it's all the values of x that are between 1 and 3. And so when you're making your argument, you could say, look, we want to figure out exactly what's in A. Because we know exactly what's in B, right? They're very clear about what's in B. You're between 0 and 6. So we needed to figure out exactly what values of x are included in A. And then however you choose to show that, you can say, look at this, and I guess I've excluded some words here, but I might say, then we can make this sign chart, this factors, and we can make this sign chart, and then there's the sign chart, and say by looking at the sign chart, we could see that the values of x that are in A are precisely the ones between 1 and 3. What do we know about the values of x between 1 and 3? Yeah, they're clearly also between 0 and 6, right? So they're in B. And that's kind of where you want to go. Does that help? Okay. Are there other questions?
Assignment
Number 3? Oh yeah, okay, counterexamples. Okay, great. So often people work harder at this type of problem than they necessarily need to when they're writing out. So you don't have to write a proof here. It's really just an illustration, or it's like a one-sentence proof, really. You might work a little bit at finding the sets you need that'll work, but I'll tell you there are probably infinitely many sets that you can find. Like, it's not hard to find a counterexample for these. But what you want to do, so we'll talk about A as an example. That in what we do for A, or like kind of how we think about it, should help help us in part B as well. So with A, this was if A intersect B is equal to A intersect C, then B is equal to C. This is false, okay? This is not true. This if-then is not true. I'm telling you that to begin with. And what we want to do is just find a single instance that illustrates that this is false. So you want to find actual sets, like list the elements. Like one set could be 1, 2, 3, 4, or whatever you want to use. It doesn't matter. But you're going to list actual elements. So you're going to find sets A, B, and C, where A intersect B equals A intersect C. You want that to be true. Right, so we're trying to show that an if-then is false. And the way you find an example where an if-then is false is where the if part of the statement is true, but the then part of the statement is false. If the if-then were true, then it would be impossible to find an if part that were true and the then part is false. So you want to find 3 sets where A intersect B is in fact equal to A intersect C, but B is not equal to C. So you want to come up with 3 sets. Make sure B and C are not the same set, but A intersect B is equal to A intersect C. The places where they overlap are the same, right? They both overlap with A in exactly the same spot, but B and C are not the same. So keep in mind, all we need is B and C for not to be exactly the same set. It's okay for B and C to overlap, right? Maybe B is the set 1, 2, and C is the set 1, 2, 3. Fine, those are not the same set. You just want to make sure that B and C are different, but that they overlap with A, their intersection with A is the same. Does that help? I would start just like picking a set for A and going from there. So pick an actual set, come up with some elements, come up with a set B that maybe overlaps it a little bit, or it doesn't even necessarily have to overlap it. The intersections could be empty. If you have trouble with this, or if you think you have one and you want me to look at it before you submit it, just send me a text or an email. I'm happy to take a look. And then, and the same with part B. You want to find sets for A, B, and C where the if part is true, where A is contained in B and A intersect C is empty, but the then part is false. So you, in this case, for part B, you want to make sure that the intersection of B and C is not empty, that they have something in common. Okay. Should we talk about Boolean algebra some more? Maybe? Don't look too excited. Okay. So we had written some Boolean algebra proofs. And we know a lot of them often involve, kind of trying to get the identity element, an identity element worked in there, and using complement laws to kind of rewrite that identity element or something. And so we're going to finish by doing a couple more proofs. We're going to prove a couple more theorems. The first one is the uniqueness of complement law. So we know that every element has a complement, and the complement has to satisfy this complement law. That each element x has an x prime complement, so that if I add an element to its complement, I always get 1. If I multiply an element by its complement, I always get 0. This theorem that we're going to show is that the complement is unique, that there is only, for each element, there is only one other element that serves as the complement. And another way of saying that the complement is unique is that we suppose there are two complements. So in this theorem, I'm calling them x prime and x star. So if they're both complements, then they both have to satisfy the complement laws, right? We're going to show that if we have two elements that serve as complements, that in fact, they're the same element to begin with. That's how we show that something's unique. So let's start. Let's suppose there are two elements. X prime and x star, such that we have a couple pairs of equations. X plus x prime is 1 and x times x prime is 0, and that I also get the same thing to hold for the x star. X plus x star is 1 and x times x star is 0. This is what it means for them to be the complement of x. We will show that x prime is equal to x star.
So x star and x prime are just there to signify that they're different.
Yeah, we're supposing that we have two elements that satisfy the complement laws
Yeah, the prime and star are just
to differentiate between the two, to make a distinction between the two elements. Yep. Okay, so now we're gonna figure out a couple things we know. So we know that x prime, I'm going to start with the x prime. I'm going to get the identity worked in, so I'm going to say that this is x prime times 1. Now here's the key. I got the identity worked in so I could use the identity laws, or the complement laws actually, to rewrite 1 in some clever way. And we always do it by choosing to rewrite it with a complement. This time I'm going to choose the other complement. Right? If x star is another complement, then that means that 1 I can rewrite as x plus x star. And now we'll use the distributive property. What do I get if we use the distributive property here?
X prime times x plus x star times x prime.
Yep. What is x prime times x? What is it?
0.
0, yeah. That is the 0 element by the complement law. And of course, if you add 0 to anything, you just get that thing right back because it's the identity. So we have x prime times x star. And this is all equal to, what did we start with on the left side of the equation, was x prime. So we know that x prime has to be equal to x prime times x star. Also, likewise, we're going to do really exactly the same thing on the other side of this line. But we're going to do it with the x star element. So x star is x star times 1. What am I going to do with that 1?
Is it going to become x plus x prime?
Mm-hmm.
So then we do the distributive.
Yeah, now we do the distributive again, and what do we get?
X star times x plus x star times x prime.
Yep. What is x star times x?
0.
Mm-hmm. And so anything plus 0 is itself, so this is x star times x prime. And what did we start with on the left side in the very beginning of this string of equations was x star. Now we are almost done with this. We're just going to, we've got everything laid out, we just have to string it together. So I'm going to start with the equation on the left side that we got. X prime is equal to x prime times x star. One thing we know about Boolean algebras is that both operations are commutative. So I can switch the order of that multiplication if I want to. I'm going to do that. X star times x prime. And what is x star times x prime equal to? X star, right? That's what we just figured out. So here we have a string of equations. Excuse me. On this side here, I've got x prime. I've maintained equality throughout. On the other side, I have x star. So this means that x prime is equal to x star as desired. How's that? So the complement of an element is unique. Are there questions on this proof before we go into the next one? Okay. When you're doing a Boolean algebra proof, you can get ideas, or at least get yourself to the I believe it stage. We're going to go through Theorem 1.4 here, and these are things that I think we can probably suss out ourselves by what the answer should be. And then we'll talk about some similarities in a context in which we can think about these Boolean algebras. So let's start. The involution law, if I have the complement of x complement, and I take its complement, what should it be? It should be x, yeah. The complement of identities law, what should be the complement of 0?
1,
It is 1, and the complement of 1?
0.
0. And now we have these things we call De Morgan's laws. So think about what we know about De Morgan from sets. What do we think we should be able to write on the other side here of this equal sign? The complement of x plus y.
Would it be
Equals
x?
x times y?
Say that again.
Equals x times y?
It does not equal x times
Would
y.
it be x prime?
Is it x complement?
Yeah,
times y complement?
right. So we can sort of distribute that complement as long as we change the operation. In this case, from plus to 10. Your microphone wasn't on, I think.
it was.
Oh, it was on. Okay. Excuse me. Okay. What about this next one?
Would it be x prime plus y prime?
Yeah, exactly. So we have these laws that work with Boolean algebra that are really similar to the laws that we worked with sets. And as it turns out, those rules of sets and set operations are an example of a Boolean algebra. So if you're trying to prove something or working with a Boolean expression, Boolean algebra is sort of very abstract. So you can make it slightly more concrete by thinking about sets. So in a Boolean algebra, or the way that sets are a Boolean algebra, I'll just do this on the side here. So we have, let's see. We have elements of a Boolean algebra. We usually call them x and y, or maybe little a and little b. With sets, we have sets, capital A, capital B, capital C, whatever. We have some operations. We can add two elements, x plus y. Over here in sets, we could take their union. We can multiply elements x times y, and over here in sets, we could take their intersection. The complement of an element is just the complement of a set. They work the same way. We have special elements in a Boolean algebra. We have the 0 element, and we have the element 1. Over in sets, those correspond to the empty set and the universal set, respectively. So I'm going to scroll back a couple pages. I'm going to come right back. So let's take a look at this equation. If I were to rewrite it and reimagine what this says, thinking about sets, this would say if I take a set A and I union it with A intersect B, I should just get the set A. Now that kind of makes sense because if I take a Venn diagram, so this says I have A intersect B, that's this set. And if I union it together with the set A, I grab everything that I've shaded at least once, then I just have the set A. That kind of makes sense. And you could kind of draw Venn diagrams really for all of this. X plus 1 equals 1 means that if I take a set A and I union it with the universe, what do we get? Thank you. What do we get if we union a set with the universe? You get everything. You get the whole universe, right? Whoops, I was about to write A. Yeah, you get the universe. If I start with everything in A, add to it everything that exists in the universe, you're going to have everything in the universe. The other part of that theorem was this one here. So if I take a set A and I intersect it with the empty set, what elements are in common with the set A and the empty set? The empty set. They have nothing in common, right? So all of these Boolean algebra equations can be reimagined or contextualized in terms of sets, and that can help get people started in writing proofs a little bit sometimes, or at least get you to the stage where you believe that it should be true, and that helps when you're writing a proof. We have one more proof to write. So this says we're going to let B be a Boolean algebra, and this one's a great proof. It says then x plus y is equal to y if and only if x times y is equal to x. This is a special, awesome, extra awesome proof because we're going to prove an if and only if, which is also sometimes signified with a double arrow. If you're going to prove an if and only if, you have two proofs to write. You have to write each direction. You have to write that each side of the statement implies the other. So let's begin. We'll do this direction first. So if we're going to do that direction, the left to right direction, we're going to suppose that x plus y is equal to y. What are we going to show?
And x times y equals x.
Mm-hmm. Okay. I'm going to invoke a previous result, one of the absorption laws. So, in particular, I think this one. So x times x plus y is equal to x. I'm going to just write that down for our reference. One point two. So we want to show that x times y is equal to x. So let's start with x times y. Now we're going to make a substitution because our supposition here is that x plus y is equal to y. We get that for free. So I'm going to substitute y with x plus y. Again, this right here is by supposition. And by theorem 1.2, x times x plus y is equal to x. So, x times y is equal to x. There's one direction. In the other direction, we're going to suppose that x times y equals x and show that x plus y is equal to y. And this time, we're still going to use that absorption rule, but we're going to use the other part of it. So we'll recall, again by theorem 1.2, recall that y is equal to y.
Is that supposed to be x plus y equals x times x plus y? We're just like rewriting.
Can you say that again?
In that first part, we recall, that x times y equals x. Is that supposed to be x plus y?
I don't, this one right here?
One more down.
Okay, there we go.
Is that supposed to be x plus y?
No, because we know that x plus y is equal to y. We wanted to show up here, we wanted to show that x times y is equal to x. So I started with x times y. And then,
Okay.
yep. So we're doing the same thing here. We're supposing that x times y is equal to x. We're going to, invoke that absorption rule again, theorem 1.2. And now we're going to look at x plus y. And we want to show that it's equal to y. In the last part of the proof, we did this first of all, we haven't used our supposition yet, right? So we're going to use this somewhere. In the last part of the proof, we use that right here by making a substitution. What substitution could we make here? Where? Okay. We want an opportunity to use this equation, right, that we assumed in the beginning of this part. Is there a substitution we can make?
We can do x times x plus y.
X parentheses x plus y? Or,
Yeah.
so what am I substituting that in for?
For the x on the right side.
Oh, well, yeah, we could, but we're not using, so I'm looking for specifically a place to use this equation that we've supposed is true.
Oh, okay.
Replace
You
the
guys
x
please
with
phone or
x
ask a
times
question.
Say that again?
Replace the x with x times y.
We could replace the x with x times y. Yeah, we could definitely do that. So this is by supposition. And what's this equal to?
Y.
Yeah, that's the absorption law. So now here we have on one side x plus y, we've maintained equality equals y. And now we can just state our conclusion. So we've done each part. I just like to kind of wrap it up nicely for the reader. So it follows that x plus y is equal to y if and only if x times y is equal to x. How's that? All right. Are there questions on this example?
How exactly was the supposition?
So in the blue box up here, right, for that part of the proof, we suppose that x times y is equal to x. That was our supposition. So whatever we suppose, we get to use whenever we want, which means that wherever I see an x, if I want to, I can substitute it with x times y. And that's what we did here.
Oh, that is
Yeah, and we did the same thing up here. We said we suppose that x plus y equals y, and then here where we had a y, we replaced it with x plus y.
right? And that was given to us.
That was, yeah, because it was an if and only if. So in one direction we got this part for free. So the supposition, that's our if statement, we get to use that whenever. And then we showed that that part was true. And in the other direction, we just went the other way around. We got to take turns. So now that was the thing we got for free, and we showed that that had to be true. Real quick, we can get some insight into like what this means here. If we think about this in sets, this says that A union B is equal to B if and only if A intersect B is equal to A. So what does the Venn diagram look like? Maybe think about it this way first, actually, because we thought about that a little bit near the beginning of during the questions part of the class. Like, what would that have to look like if A intersect B is equal to A?
B would have to be 1 for the universe.
B does not have to be the universe.
Would A have to contain B?
Other way around. A is a subset of B. B has to contain A.
Inside of B.
Yeah. So if A intersect B is A, that's the same as saying A union B is B, right? Like, taking the union of A and B doesn't add anything to B, right? A was already in there. Okay. All right. So that's just, we're just about out of time, so we'll adjourn for the day. If you have questions, text or email. Otherwise, I'll see you all either in person in Williston or on Zoom on Wednesday.